Good morning, everybody. We're just going to wait half a minute to give people a chance to filter in, and then we'll get started. Thanks for your patience. All right, I'll go ahead and get started while people are trickling in. Thanks for joining us for the October US MAP webinar. My name is Harrison Dreves from the National Renewable Energy Laboratory. I'm going to be running the webinar from a technical aspect today, and I just have a few quick housekeeping items before we get to the good stuff. Just so we know, we're going to have a lot of people on today's webinar, so everybody is unfortunately muted. You do have two options to listen to the audio for today's webinar. Computer audio, which is the default, works great for most people, but sometimes people have issues with that. If you're one of those people, we recommend listening by phone. You can click the Join Audio button in the bottom left corner and choose phone call, or you can leave and rejoin the webinar and choose phone call as the audio option when you connect. If you're having technical issues with your audio you can't resolve or with any other aspect of the webinar, please just message me using host in the chat panel. That is the single dialog bubble. For questions, and we are going to be doing questions at the end of today's webinar, please use the Q&A panel. That is the double dialog bubble. So single bubble for technical issues, double bubble for questions. And we're going to try and get to as many of those as we can. All right, with that, I'm going to hand it over to Joe Barry, who's going to introduce today's speaker. Joe, take it away.
All right. Well, welcome, everybody. It's my pleasure to introduce Dr. Timothy Siegler. Tim is an ORISE Fellow in the Solar Energy Technology Office, or SETO office. He grew up, academically anyway, very close to where I grew up as a kid in wonderful Michiana, attending Notre Dame University in South Bend. Very close to where I grew up. From there, and getting his degree in chemical engineering, if I remember correctly, he went to the University of Texas at Austin, where he worked with Brian Korgel and did some work on, some really interesting work on some wide gap based metal halide perovskite systems before subsequently graduating and working a little bit with Hugh Hillhouse. Some recent work that I know that he was a part of involved using ML approaches to understand perovskite materials. But since then, he's joined SETO, and he's here today to talk a little bit about an article that he and that office published in ACS Energy Letters, outlining kind of the SETO portfolio. So with that, I'll turn it over to Tim.
All right, thanks, Joe. Thanks for the kind and comprehensive introduction. Yes, I've joined the dark side in the last year. So today I'd like to discuss a perspective that our office published recently in ACS Energy Letters, and a little bit about the strategy that underlined, why we published this piece, where it is, and what the maybe implications for folks, particularly in the nascent startup community in the United States, would be. And before I get started, I'll have the opportunity to thank these people profusely throughout, but wanted to thank all my co-authors that helped to contribute to make this a powerful consensus statement. Andrew Dawson, as many of you probably know him already, he's left for OSED, but he was fundamental in developing the actual strategy that we communicated in this piece. Peter, David, Marcus, Garrett, Lenny, all made big contributions here and have continued to make contributions to our perovskite strategy within SETO. As far as where the sort of outline of this presentation goes, I think before I get into perovskite specifically, I would like to level set and take a step back, look at the higher level view of what SETO is and what our goals are as an office before we get into the opportunity for perovskite PV to feed into those goals, the perspective piece itself, and then some goals and takeaways. And so the Solar Energy Technologies Office is an applied technology office, one of several within the Energy Efficiency and Renewable Energy wing of the Department of Energy. Our office specifically accelerates the advancement and deployment of solar energy technology in support of an equitable transition to a decarbonized economy no later than 2050, with an intermediate goal of a decarbonized electricity sector by 2035. We do this in a number of different ways. We drive innovation in technology and soft cost reduction to make solar affordable and accessible. And this is where a lot of our research and development work happens, especially for panel technologies of all kinds. We enable solar to support reliable, resilient, and secure grids with high penetration of inverter-based generation to make sure that grid performance remains high for consumers and users, and support job growth, manufacturing, and the circular economy in a variety of different ways throughout the entire solar industry. And since we have these really aggressive, we're trying to enable very aggressive deployment goals. We commissioned a solar future study 1 year ago. It got published. It basically identifies what levels of deployment solar will need to have in order to enable a fully decarbonized electricity sector by 2035 and energy system in 2050. Now, this is a really well done report, and Raul took a lead in this as well. And I, will not claim to be an expert in the methodology or how this modeling was done, but I will just, basically go over high-level results and talk about the 3 scenarios that were modeled, where we have a completely decarbonized electricity grid by 2035, a decarbonized electricity grid by 2050, and then a fully decarbonized energy system by 2050. And I will say, we aren't assuming the 2022 electricity mix throughout this entire time. We assume that vehicle electrification happens at a steady rate according to trends and future market projections, right? We aren't doing a business as usual case, but it's more of a no action versus aggressive action case for the 2050 sort of end goals. And I think the take home point, now 2020 was the base case year because it was a 2021 published report, but the already rapid growth of the solar industry, looking at 2020 deployment levels from 2015 or 2010, it's a very impressive feat, need to continue to grow exponentially until we get about a terawatt, and that's AC, by 2035, and 1.6 terawatts by 2050 for a decarbonized electricity sector. Energy sector gets a little higher, 3 terawatts by 2050. And if you talk about year-over-year deployment, right, let me just describe this chart very quickly. Each one of these squares represents 1 gigawatt AC of annual deployment. This is not cumulative over this time range. This is year over year. You see that in about 2020, we deployed about 15 gigawatts AC of solar, which is a very impressive feat. But starting last year into 2025, in order to hit these full decarbonization scenarios, we need to deploy nearly 30 gigawatts AC, and we fell quite short of that in 2021. Who knows what happens in the next 3 to 5 years. Moving forward then, in 2026, another step change is needed to nearly 60 gigawatts AC of solar deployment and over 60 gigawatts by 2031 to 2035. So we need rapid deployment. Deploy, deploy, deploy is the, that is kind of the motto of the day. And while our office doesn't directly account for deployment and does not do deployment, we need to help to enable these levels through R&D and all the things I talked about earlier. This is not just solar. Wind and storage also need to play their part, but solar needs to play a significant leading role in these decarbonization scenarios. We enable this through a division of labor that can be described by 6 different teams. Photovoltaics research and development is where I sit primarily, where we enable R&D that advances photovoltaic technologies to improve efficiency, reliability, lower manufacturing costs, and drive down the cost of solar. Manufacturing competitiveness is another. It organizes the tech to market activities within SETO specifically, and is another office that many on this call are likely familiar with and engaged with, as Andrew Dawson was sitting primarily on the manufacturing competitiveness team. We also do a lot of other activities as well. We continue to work in concentrated solar thermal, maybe not for continuous steady state electricity generation, but as a sort of generation plus 4-hour storage technology, or maybe to do industrial process heat for deep decarbonization. Systems integration to enable that, again, inverter-based technologies will be able to deploy steady AC power to the grid with high levels of solar and wind penetration, but primarily solar. And we do soft costs as well, doing strategic analysis and institutional support for permitting, dual use and other applications, as well as workforce and equitable access for community solar and workforce development for the rapidly growing solar industry. And to enable this 5 times rapid deployment, we have some high-level goals that we want to be hitting by 2030. I think we want to, and some of them are more soft, or some of them are more systems integration or soft cost related, where we demonstrate reliable operation of the grid with 75% inverter-based generation. But a lot of it comes down to driving down costs to 2 cents per kilowatt hour for utility scale photovoltaics, and for other markets, allowing 100% of energy consumers to choose solar without increasing their energy costs by 2025, which I think is beautifully comprehensive to, for equitable access to cheap renewable solar electricity. And so with these high-level goals in mind, Perovskite PV has the potential to maybe help with these 2035 and 2050 targets. There has been, the academic community has demonstrated the headspace for over 25% efficiency single junction and 30% efficiency tandems, with the potential for low production costs and very low capex, and rapid production capacity expansions as a result of this lower capex. And again, while it's on very, very small device areas, less than 1/10 of 1 centimeter squared at this point, there are many of these advancements. There has been, a lot of work to drive up efficiency to very high levels and demonstrate a high headspace there. There's been a lot of good work showing that while stability, is a concern, it's something that there's a lot of levers you can pull to enhance stability and to enable through high throughput manufacturing with a potential domestic manufacturing advantage. SETO observes that there are 3 major categories of perovskite technologies that are currently being explored for commercialization in the startup communities and in various for-profits. A single junction, which is a standard PV with a single perovskite absorber, which has potential for the lowest dollar per watt costs of any of these 3 that I'm going to mention, and a current record of, again, 25 and some change on less than 1/10 of 1 square centimeter. We'll talk about these targets later, but DOE has identified a higher target of about 18% efficiency on 500 square centimeters. Perovskite tandems allow for higher efficiency with the same sort of capex advantages that a single junction device would impose. However, because you are doubling up the number of absorber layers and have to double much of your capex equipment, we have a higher target of 24% on 500 square centimeters, with the current record of about 28% reported in Martin Green's tables for less than 1/10 of 1 centimeter squared. And then perovskite hybrid tandems are a tandem that employ perovskites in concert with silicon, CdTe, or SIGs, which has the potential for the highest efficiency, and currently exhibits the highest record efficiency of over 31% on a larger 1 square centimeter perovskite silicon tandem cell. And DOE has a target of 27% on 500 square centimeters. And so to discuss what our office thinks about perovskites, we published, again, a perspective letter in ACS Energy Letters. And before we get into the actual details, while there were a lot of implications and a lot of things that maybe could be perceived as takeaways for the startup community and for-profits, publishing in an academic journal was not an accident, and it was intentional so that the large community of applied researchers, obviously fundamental research is very important and something that we value, but there's a lot of applied researchers who want their technologies to be that they're developing, or their solutions, or the science they're working on to be helpful to decarbonizing the US economy. And so attempting to create some high-level alignment among academic researchers on these high-level topic areas, and clarifying which questions, at least that DOE perceives, are actually gating for deployment were some of the higher level goals of this paper, as well as some stakeholder engagement, right? I think, perhaps folks who are very familiar with our office and know SETO very well might not have gotten much new information from the paper itself, but there is a larger community beyond the DOE bubble that we wanted to reach and to communicate to, people that we aren't talking to every quarter in quarterly update meetings, who still could contribute quite a bit to to perovskite technologies. We also valued the feedback from the peer review process. And I think one thing that we maybe didn't anticipate is how much communication and how much feedback and dialogue we were able to generate. That's been very productive, very useful, and something that we very highly value as a result of this paper. In this paper, we largely discussed this triangle diagram, which many of those who are familiar with our office are probably overly familiar with, sick of possibly at this point already. The major techno-economic barriers that we have for deployment, stability and durability, efficiency, validation of bankability, and manufacturing. I'll go over these in a little bit more detail one by one, but again, wanted to just thank all of my co-authors, as well as all the people who I was able to talk to in one-on-one scenarios: Michael Kempe, Paul Visor, Ingrid Reppens, Nikos Papadakis, David Feldman, Leah, and Christy, who all helped with various parts of this paper and getting it out the door, and had valuable contributions to this work. And so going through this diagram, I think I'm going to go to a maybe basic or obvious level to some, but just to make sure that we're all on the same page, discuss why each of these are particularly important, right? Obviously, stability and durability are important, but I think it's, when rubber meets the road, when thinking about deployment, again, SETO's goals are deployment focused, to enable high levels of deployment. It's important that a consumer, whether it's a customer or residential consumer who wants to install solar on their rooftop, or debt-based financing that's putting money into a special project vehicle for financing a utility scale field, they need to be assured that the investment they're putting in will generate enough electricity that they can perceive a return on their investment in terms of value. And that usually comes in terms of a balance sheet that gets the return on their investment that they're looking for. As far as the technical challenges around stability and durability, they're obviously very multivariate. These are all different potential stability issues that have been identified in the literature, or maybe most of them for perovskites, but some of them for other materials as well, like silicon with corrosion of back sheets and things like, and various things. And while some of these are more important, a lot of these are less important, and it's I think an important benchmark for folks working in the R&D space to utilize outdoor testing to help focus from this huge morass of degradation modes to what is most important and what is gating. Now, the community has done a really good job, and I think there's a handful, 2 to 5, that are the most crucial. We've identified, the community has identified and is working on in a lot of detail, but nonetheless, this is using outdoor testing, even if you can't employ it in yourself in your own labs, talking to folks who are deploying outdoors and figuring out what they're seeing, what the most important degradation modes are, helps to focus research and make sure that the questions that are being asked around stability and durability are most impactful and utilizing resources most effectively. As far as efficiency is concerned, I'm working to rebrand efficiency internally as efficiency at scale. I'm speaking as myself here, not as the DOE, but if I don't see that 25.7% record on 0.1 square centimeters broken ever again, I think I'm okay. It's more important that we get to near 25% on larger area devices. And to kind of level set for the community, right, I think silicon cells, right, have a standard cell size of 274. That's what an M6 cell is, if I'm remembering. It's either 274 or 276 square centimeters, and are actually moving to larger formats. We will see if the market bears that, but nonetheless, this is kind of like the orders of magnitude increase in cell size that we're looking at, not to mention modules as well. And when we look at the cell efficiency module gap, I think there's it's obviously scientific problems that may or may not be contributing to this area, this gap in efficiency between small and large area devices. Maybe some of the quote unquote benign defects are actually becoming more apparent at larger area. Perhaps sheet resistances of, let's say, metal transparent conductive oxides that are tolerated at very small area become more problematic when you go to larger area devices and cause a lot of series resistance. There's also process uniformity and wetting concerns that could be happening where, I know there's in some research labs, there are for dot cells a large percentage of quote unquote outliers that you would throw away because there's a pinhole or some sort of defect in the device that ruins one of your 0.1 square centimeter devices. You imagine as you go to larger 110 square centimeters, those defects that will appear in your small area samples will become much more prominent and have a higher frequency of module or like cell failure, excuse me. And then potential compositional heterogeneity as well. Areal heterogeneity, which means in the XY plane, or at various length scales. It could be millimeter to meter level heterogeneity due to variations in just being suboptimal in your deposition, or it could be on the micron scale or even on the nano scale, depending on whether there's phase segregation, either photo-induced or inherent phase segregation in your perovskite compositions. But I think it'd be remiss to not discuss some of the systemic issues. A lot of these records are optimized on non-scalable techniques. Even if you want to try to make the argument that spin coating has scalability potential, the way that you do solvent anti-solvent engineering in a lab is probably not going to be useful on substrates that are larger than, let's say, 2 inch by 2 inch, maybe being generous 5 inch by 5 inch, but probably 2 inch by 2 inch is about as large as you can get, doing specific anti-solvent dripping in the center of a spinning sample and getting the fluid dynamics such that it perfectly and consistently makes uniform thin films. This is something that's being solved in real time. And so this is not as big of an issue as maybe it would be 2-3 years ago. But academic breakthroughs often aren't tested on larger areas, or perhaps 1 square centimeter is defined as a larger area. And again, thinking about the competition, the other technologies in this space, CAD-TEL and silicon, they're in the 100 square centimeter cell size. And so the definition of large maybe needs to be explored as well. And then limitations and best practices as well. Now, this is a very broad catch-all, but I think I want to, just take one example that I perceive that maybe could be used by academic communities and folks making small area samples to really help with some of the, to test on larger areas. And, let's take a standard pinout that many are familiar with and assume that one of these, let's take scale bars such that one of these squares is 0.1 square centimeters in size, and assume a perfect mask where you're just exactly masking the active area with nothing around like micron level precision. By doing very small adjustments to your shadow mask and keeping all the pins in the exact same place so you don't have to change anything in your testing equipment, you could utilize this large exclusion zone that happens around, that's present around all of your devices, sample much more of your area, right? You or your grad students have done the work to make these films. Let's utilize all of them, and more than double the active area just from a very simple switch without changing any of the processing at all. Moving on to manufacturing, obviously manufacturing, the processes themselves are important in optimizing those, but there's also a lot of, manufacturing considerations related to quality control, related to process uniformity, repeatability, throughput, making sure you have inline metrology, and doing supply chain development as well. I think I'm going to focus on the process control and process insensitivity, which is, I think, very important, right? Because to enable the low costs of perovskite manufacturing that would help with SETO's ultimate goals, low capex is the promise that perovskites may be able to achieve one day. But the tighter control windows that adds cost, all of that. And so process insensitivity helps to maintain headspace for cheaper manufacturing of perovskites. And I think to call out a number of different things that may require process insensitivity. Precursor ratios and concentrations, whether that's in a solid or an ink, are important. I'm thinking of, I believe it was Jana Vanzov's work on lead acetate to methylammonium iodide ratios for that specific anti-solvent-free composition, and how tiny fluctuations there yielded dramatic results or differences in PC values. And so processes that require such tight controls might have a very high failure rate for modules and not be particularly attractive for high volume manufacturing. Storage time on the order of days in case there's a line stoppage, or even just standard, trying to mix a lot of material at one time, or get a lot of material prepared at one time. In order to, if you have to continually throw away inks or solids and replace them, that's a yield loss in and of itself. That has nothing to do with the deposition. So being able to store your materials for a few days is important to make sure that you keep yields high and by extension costs low. Similarly, handling time in the course of hours, so you don't have to continually flush out your lines or throw away material when, again, there's a line stoppage or something unexpected happens, and which that would impact yield as well and create extra hassle and time on the manufacturing line as you handle that specific fire and need more time to do that. Ambient temperature and environmental conditions as well. Being able to produce solar cells with the same efficiency in the hottest, most humid day of the summer versus the coldest day of winter, and getting the same performance regardless. That's obviously very important when you're trying to do gigawatts of throughput every single year. And then various different deposition parameters as well: feed and vapor pressure, contact layer heterogeneities, line speed, and substrate temperature. Being able to employ design of experiments and statistical process control to verify that small changes in all of these are very, very important, so that there's, there's statistical power behind claims of process sensitivity or insensitivity. And finally, anti-solvent treatments and compositional heterogeneities downline. If there's tolerance to that, that helps with yield and performance as well. Finally, validation and bankability is the last part of this sort of conceptual diagram. And bankability is a thorny question, right? I'm frequently asked, what is bankability? And so I go to some of my colleagues who have spent, decades in the industry and with First Solar, et cetera, and ask them what bankability is, and they tell me it's a thorny question. So I will try my best here to really figure out what help you figure out what bankability necessarily means. So I think at its base level, if I had to come up with a one-sentence definition, that from my understanding, it's the ability to secure investor financing with reasonable interest rates. Now, I think there's two ways of thinking about bankability that folks in this audience would be considering. I think there's business bankability, right? How bankable are you as an investment to venture capital, to various investors that want to put money into your organization? But from SETO's perspective, we are looking at end use and deployment. And so I'm going to be presenting bankability from a project finance perspective, where you'd want bankability of the project that you are deploying to make sure that that is bankable, and that the folks who are putting money behind, a utility scale field with perovskite panels, or maybe even just a consumer who's trying to put a perovskite solar array on their house, what they would be potentially thinking about, or what the insurance agencies who they'd be leaning on for support would be thinking about. And to take the wild morass of bankability and try to get it to as sharp of an Occam's razor as one possibly can, I've seen this sort of three major risk categories framework. I think it's interesting and important. I think it's a very useful framework to be thinking about bankability in. As product risk. Product risk is going to handle and tackle a lot of the challenges that we've discussed, the techno-economic challenges that are more technical in nature in terms of performance and stability. But at the end of the day, what a developer will be looking at is, can this perform at levels that are commensurate with state of the art? And that's the question they're ultimately going to be asking. As far as reliability, right, has the product undergone due diligence of a standardized test set? I think there's two levels here. You want first panels that have passed a specific standardized test set, a full test set, not just a damp heat test, but a full, set of tests. And I think also, word spreads fast. If a specific standardized test set is not sufficient to probe all the major degradation modes of a specific type of technology, that will, be something that will spread like wildfire through the developer community as well, and contribute to product risk if you're not testing using the right set of standards. Market risk as well. Is your supply chain reliable? For a developer, what that's going to look like is, well, I'm trying to construct a utility scale field as quickly as possible. I brought in all these construction workers from across the country, and I don't want them sitting around twiddling their thumbs. Will we be able to stage these perovskite panels and have enough of them to keep my, my men, women, and non-binary employees ready, working 8 hours a day through the day, and get everything when we need it without any sort of additional cost or additional lead times. And I think there's a second market risk related that actually plays into the company related bankability issues that I was talking about earlier. And is that if there's a 25 or 20 or 15 or 10-year warranty on these panels, and a panel fails before then, maybe there's a record hailstorm or something happens, and well, I guess in transit would not be necessarily that big of a concern, but things happen, right? Warranties exist for a reason. So will the panel manufacturer be able to honor that warranty when it happens when something happens to a panel several years down the line, right? Because a warranty claim for a bankrupt company is not, someone else has to take on that liability because the company's not there to anymore. I think the final one is project risk as well. And this relates to stability in a way where required ROI times need to be achieved prior to module failure. The balance sheet needs to work out for these project financiers to make sure that they are getting the returns that they want on these investments. And I think this is also where lead issues might be able to, might rear their ugly head potentially. And I think there's deployment risk, right? Decommissioning and reclamation risks are included in the upfront cost in almost every regulatory frame, set up in the United States. Reclamation, decommissioning costs are paid up front by developers. And lead flags might show up in increased decommissioning costs that would raise the cost of solar deployment at that start point, as well as insurance claims, which that would be how, if there is something that leaks, that could be something as well that causes some issues as well for the developers. And there's also perception-based risk. Community pushback and anti-solar messaging has already latched on to certain elements. There's cadmium telluride panels, and there's lead in the solder or silicon panels, and this is so we already know that their anti-solar messaging and community pushback are things that could potentially gate deployment in various communities, particularly communities that aren't particularly amenable to solar. And so this is something that would classify as project risk in the bankability profile for a project. Looking at our total awards, this is some analysis I did. A little bit, just quick notes on methodology. These are all active awards as of April of this year. And I took data from the RPPR2 reports. So anybody who is a current awardee with us or a past awardee, please make sure you fill out your RPPR2s correctly. We do use them. But based on that, divided each project into a fractional effort and then identified a total sum fractional effort into each of these areas. I think this is a pretty good balance. The slight underserving of bankability in favor of manufacturing, I think, is warranted given where the perovskite industry may be right now. And I think as well, giving a more bankability work to national labs versus more manufacturing to for-profit and non-for-profit entities that aren't national labs, I think is also a sign that we're doing a reasonable job with our distribution. And just to highlight how, what we're saying is brought into action. How do we fund work in each of these areas? Bankability, obviously our crown jewel of our bankability portfolio is the PACT Center, which is this coordinated effort between Sandia and the National Renewable Energy Lab, Laura, who is, they do a lot of different efforts, but they have these outdoor deployment campaigns that are super important to tackle thorny durability questions. They then do performance test protocol development and try to develop a test protocol set that is going to be representative and will be very useful to product developers as they pursue bankability of their projects. You know, if PAC comes up with a test protocol that is comprehensive enough to be used by these various entities who will be doing risk assessment like that, that is something that's going to be potentially very useful, we hope. Then also bankability programs and bankability services that in coordination with Black & Veatch, who is a member of PACT as well. Efficiency at scale. Now, as far as these specific projects I'm choosing to highlight, you know, all of the projects in our portfolio are excellent, and we are all very happy with all of them. And if you're not, you know, you get our quarterly reporting, you know who you are. But no, jokes aside, we are very happy with all of them. I just want to highlight one or two to really indicate like how we fund our mindset in funding in these areas. Something related to efficiency at scale. This is a collaboration between MIT and Stanford University that utilized Gaussian process regression to optimize high throughput manufacturing of perovskites and benchmark these machine learning methodologies against more traditional methods of optimization that were, you know, that did not employ machine learning. And I think there were two really interesting results from this benchmarking. One is getting to 80 to 90% of optimal happened with a third of the experimental iterations. So a huge potential for increasing cycles of learning using these approaches. But then that last 10% was a little bit more challenging. And so potential for refinement of these machine learning methodologies to get you to near optimal at the same speed that you can get to 90% optimal. For durability, there are a lot of durability projects in our portfolio, but two that I think you know, help to identify potentially new ways of thinking about durability for perovskite solar panels is some work that we from the McGahey group at the University of Colorado, talking about reverse bias degradation and how rapidly that may occur, which will be potentially important if there's partial shading on a module that shades a individual cell completely. And then some work from Princeton and Barry Rand on sort of iodide and iodine electrochemistry, as well as just using electrochemistry to probe degradation, voltage thresholds of degradation in a device stack. Finally, manufacturing. We have funded manufacturing for a lot of different for-profit entities, and this is a sampling here for you all today. And so, as I reach the end of my time, just some quick goals and takeaways from this piece. Again, you know, this is a perspective that was intended to try to get academics to think and adopt a mindset of what will it take to deploy, and hopefully try to reframe a lot of the questions they've been thinking about and they're curious about scientifically in light of these challenges that are going to be you know, going to continue to pop up in the perovskite community as they develop. First, just a general set of RFI targets. So this was something that we as an office put out late last year into early this year. It was a collaborative sort of RFI that we set in collaboration with the community based on where perovskites were as a technology and based where competing technologies like silicon were. And we identified certain aperture area PCEs on 500 square centimeters. I discussed those earlier, as well as an initial set of durability tests, which was, you know, because PACT had not been able to do a full development of their test sets. This is just an early kind of guess, but this guess is also validated with some outdoor testing as well, with 1 kilowatt total of sample just for statistics reasons. So these are kind of the outputs, the goals that we're looking for, or that we think are, no, we're not looking for, that the Department of Energy think would be useful for the community to pursue. And as far as what we've seen so far, there are approaches at this. I think Oxford PV in the UK recently validated at Fraunhofer 26% and some change on an M6 size. I believe it was 274 square centimeters, but I could have that slightly off. But having all of these together is something that we are unaware of as of right now at the DOE. And finally, because this was targeted at the academic community, DOE obviously has a large visibility in a lot of different academic work. And so we have a couple sort of hopefully low lift ways that folks in the startup community will be able to enable external R&D work to help work for their company. Just suggestions and things that of ways to help leverage this huge amount of work that's happening in academia to be more useful and more helpful to solving some of the challenges that you all are facing in your day-to-day. I think one thing that's important is trying to standardize form factors. I mean, shadow masks and test pinouts are, I think, very important things to standardize, but there are other parts of this as well. Degradation chambers and procedures, shipping procedures, and how you validate whether something gets damaged in transport. Like having standardization across all these different aspects allows for really rapid collaboration, as you don't have to spend person hours attempting to create synergies where they don't exist between two different groups that have entirely different ways of making devices that are kind of arbitrary in the differences. Again, when I say training resources, I don't mean putting on full trainings or putting a lot of time into this, but I think a lot of academic a lot of folks in academia are interested in moving up to module level research. That's very encouraging because there's a lot of potential degradation and a lot of durability issues and various other issues that could and do manifest when you go from a single cell to a interconnected mini module. But this has some issues too. I mean, I think we see a lot of repeated efforts for scribing and packaging of all these different things. And I think, obviously some of that for scaled up full size devices are going to be incorporated into IP, but for lab scale, small area devices, maybe not, for benchtop laser scribing systems, maybe that's not quite as important to core business goals. And then also we see that there are some limitations in folks trying to bootstrap their own homemade environmental chambers. We've seen some great successes in making environmental chambers from scratch for very, very cheap that allow for long duration testing. And I think better communication across these, in this specific area is something that could be really, really helpful and really leverage a larger community to get as much more high throughput, long duration testing. I think as this becomes even more important as perovskites become more stable, right? Because as your material gets more stable, the tests become longer, your throughput gets lower. So finding ways to scale this up and make more inexpensive homemade environmental chambers is something I think is quite valuable, would be quite valuable. And finally, being vocal about what's relevant, right? I already talked about, this academic community we have in the United States, is fantastic. And they all, again, there's a great desire to be useful and helpful to industry. And so a lot of literature best practices might not be starters for your company. And so making strong, consistent feedback will help researchers be directed and stay focused. And I think that could be potentially helpful and useful as well. And so just to conclude, so SETO has a history of funding perovskite R&D and plans to continue into the future, pending funding levels and congressional direction. And we fund perovskites with our office mission in mind, right? What work needs to be done if perovskites are going to make a difference in 2035 deployment targets. Before I turn the floor to question and answer, I have two quick plugs for everybody. One is a plug for the position that I currently hold, the ORISE Science and Technology and Policy Fellowship. This is a fantastic training opportunity and fellowship opportunity for a early career person such as myself. It's not a fellowship that, it has a very competitive salary, It's usually 1 to 2 years, usually 2 years. You get a lot of great mentorship and a lot of great visibility and connections. I'd recommend for any professors who happen to be here, recommending this to your students. And even if you don't want to work on perovskites, or you don't want to work on PV, even, we have a wide range in our office of things to work on. All of them are fascinating, I promise you. You can apply at any time, but our deadlines are January 15th and July 15th. And so that's when we will begin doing our internal review. And that we intend to do that year over year for the foreseeable future. Then finally, for everybody, make sure that you sign up to our energy.gov newsletter. This SETO specific newsletter at this link here identifies what our major activities are as an office, what our major outputs are as an office, and helps keep you up to touch on what we're doing. And keep an eye on us, because I think we need to, people keeping a good eye on us. So with that, I'd like to thank, of course, all the co-authors that I've already thanked, and everybody who helped with the paper. Also, all the other staff who have contributed and helped with perovskite strategy and just helped me in general. And then finally, have one final disclaimer related to my ORISE fellowship, right? That me and David Ung are both fellows. The appointment within ERE is sponsored by the DOE, but administered by Oak Ridge Institute for Science and for Education. And opinions expressed by us individually are the authors and do not, or presenters, and do not necessarily reflect the policies and views of DOE. So with that legal disclaimer out of the way, I'll hand it over to Joe for questions.